master student working on this topic. And then I established a collaboration here with Peter down there at NIMS here. Because, well, this is the place you have sun. We don't have much of it up north where I come from. So this is probably a very good place to start working on sun energy. Okay, that's kind of the background. Here's a little bit on what it is. As I said, where is this again? Yeah, there we are. This is a very simplified scheme of a solar cell. You have the sun coming in here. Think of each of these dots as a photon. What a photon does is it rip out an electron from one of the molecules here. If you do that, the natural tendency would be for the electron to sort of get into the atom again, and not much happening. But if you do this in a clever way, and with the way they typically do it, is they have two different kinds of semiconductors here and there, an N-type and a P-type. And that makes the electron not merge again. I don't understand the physics completely here. But you get a surplus of electron in one place, and you got deficit on the other semiconductor. And that sets up an electric field. And you got and the electron starts moving, and you got the current here. And you can light up your bulb here. Two things is necessary for this to work well. First is you have to have a lot of sun, the solar irradiation. And that's what you have basically all over Africa. You might think there must be most close to the equator. That's not necessarily so, because here, close to the equator, it's like today, usually quite clouded. And the limiting factor, besides where the sun is the cloud cover. Cloud cover reduces irradiation. So up here in Sahara, no clouds, almost no time. That's really the perfect place. But on the other hand, not many people living up there. So probably Ghana down here is a pretty good place for having solar power. Now, this is basically irradiation data. And they can be measured, and they are measured. Not much you can do about that. But the other thing you can do about is how you built this solar cell. And as I said, my schematic thing, there was two semiconductors, you glue them together and you get this thing going. But there is a million things of doing it. This is a slide, one of those slides you're told you should never show because no one can read it and no one really understands what it is. I just put it here because I meant to show you how many different ways there are of making solar cells. Each of these dots here is a specific solar cell. And the thing is, there's a timeline down here. And the thing is, if you follow one here, you see it's the same technique for building solar cell and the same material only with technical improvement. And you see there's a technical improvement for all of these as positive derivative. So they increase by time. But there are not a million ways of doing it, but there are many, many ways of doing it. Of course, making one of these dots is probably man-hours or man-years in a laboratory to tweak and treat all this thing here. So you should try to simplify all these experiments and all this hard work in a laboratory if you can do some simulation of this thing. So you at least can throw away all those, obviously, that won't work. Of course, by the end of the day, the real test is if it works. So you have to build a prototype. But a simulation tool would be very nice to have. So see if you can get this working. So that's basically the background. So what I will try to cover in this talk then is first to establish a mathematical model of how this this solar cell works. And then I try to solve some specific problem with that model. And then I will discuss some of the numerics we work and show some numerical results for it. And I wrap up with a conclusion and some ideas of future work. We have the situation. We have ripped the electron out of its valence bond there. And then in an electric field, it experiences a force, plus or minus depending on how we define the direction of this electrical field. And you can simply use Newton's second law, and you find that the velocity of that electron is written like this. Q is the charge of an electron, and m is the mass of the electron, and tau, the mean time between the collision of electrons here. These will be constant then. So we lump all those constant to a mu here. Now that electric field that sets up here, that is the gradient of the potential. And that makes we have a drift flux like this. While this is for one electron, we think of n now as a density function of a lot of electron, which might be spread out at some, and we only really in one dimension here. Maybe I'll show that. Because the only direction that matters is that one across the boundary here. So we can think of this as one-dimensional, really. That simplifies life a lot. So that density of electrons depends on where we are on that axis. And of course, this is dynamically, so it changes as times go. So the total flux then, or the drift induced flux, is then given by this thing here. Now, drift isn't the only thing that, sorry. Oops. There we are. Are we? Yeah. There is also a diffusion-based flow. Up. And that's written like this. The two nu constant is another physical constant, the Boltzmann constant. And then also comes temperature in. Temperature here is in Kelvin, so it's only weakly dependent on the temperature. But notice that it's proportional to that too. So you have a diffusion-based flux, which can be modeled like this. That gives the total flux equal to this expression here. And notice we now have two things that's linked together here. We have, this is the flux, subscript n means that it's the flux that's on these electrons. That depends on the electron, the numbers of the electron, and the gradient, as we have it up here. That's this up here. But it also depends on the potential. And the potential itself depends on this density function of electron. So there is two unknown, the phi and the n, and they are coupled in two partial differential equations. This is a simple Poisson equation. That's linear, and I didn't really put up the full equation here. That you can argue a similar way for if this was the electron, the opposite, the positive thing, is usually in this business called holes and denoted by P. And you have a completely similar equation for that. So you have a standard advection equation here, which is dominated by the flux here, one for the electron, one for the holes. And then the net flow here will be the electron minus the holes, and that determines this potential through this Poisson-like equation. And that was the equation we had for the flux on the previous slide, and a similar one for the holes, where we have hidden a lot of this constant that comes up into this. We have lumped them together in this constant here, and likewise here. So that's basically the model. And that's a pretty standard model used, not only for modeling solar cells, but for, in other technical devices where you have an electron flow and that sets up an electric current. Then you have this drift diffusion model here. So that's the basic model that can be used in many cases here. We will use it for a special case. Here I have a little bit more detailed solar cell like this. I have my N-type semiconductor up here, made of some silicon, typically made of silicon, and another P-type silicon thing here. On top of that, facing the sun comes in from top here. There is a silver layer thing here, and between here, that top silver layer and the first N-type semiconductor, there is a thin glass layer. That one is blown up and shown here. So you have silver on top, that thin glass layer, and here comes your semiconductor. And really what we want to show, simulate, is what's going on from this boundary to that. So it's only a tiny bit, really, here. And, yeah, should also say that we assume we have a steady inflow of photons hitting in here. So after a while, we'll reach a steady state. And it's that steady state we want to simulate. And that implies that the change in that density should be zero. That must mean that the flux is constant. This was the equation for the flux, and that's your constant flux. So J is some constant here. Then we have the Poisson equation, which gives the connection between the potential and the density function of the electron. And here we have lumped all this nu in here. That nu is a mix of physical constant like the electron weight, mass, and Boltzmann constant. And it's also some material constant. There's a material constant epsilon here, which is the permittivity of this thing here. And there's also the L, which is the thickness of this layer. And yeah, N1, that is something to have to, that's a scaling factor, essentially. And it's the scaling such that we sort of fix the boundary values at the outgoing bound to be 1. We have also, the reason this L comes in here is that we scale the length such that we're integrating from 0 to 1. That's our size of that. That's why the L comes in here. But it's nice to have that. So when we start modeling this thing here, changing nu, that's really changing the material here in some way. For this thing to be something to solve, we now got rid of time, so we need boundary conditions. We have fixed this to be 1. That's just a scaling thing, that N1. So the interesting is at the incoming boundary. The incoming boundary, the top layer, that could be something different. But typically, and that, should I say, what that alpha is depends on whether you, like here, you have silver and silicon, or you are here in between where you have silicon, glass, silicon. So it's two different regimes there. And that really you will see in this alpha typically. If you have silver, glass, silver, you expect this to be close to this, it be the same at both boundary. So if it's 1 here, it's close to 1 there too. Not necessarily so when you have silicon on top. And then this is the strength of the potential you're able to set up. Yeah, so we just want to solve this thing here, and it's not too difficult. The main difficulty is, of course, there's a nonlinear term. Yeah. But first, maybe a comment on what that constant flux is. I put it in quotation marks up here because it's not really, depends on what you mean by constant here. You might, if you look at it, you might see that you can rewrite the first equation like this. It's easy to, if you start with this, just take the derivative and you see you end up with the first one. And if you now can assume that j is independent of x, you can rewrite it like this. Just divide by n there, and you integrate, and this is what you get. Oh, shit. Where are we now? Yeah. But if I really believe what I'm saying, that j is a constant, then these two, phi and n, they are both dependent of x. They are not constant, but they must but they are linked like this to a constant like that. So if they are the same, this sum is the same at all possible x value. Why not pick the next value where you know the values of them? And you do. You can pick the left boundary. And then there the value was that bow-faced phi and the alpha. So you can plug in that and you can use it here. Still, there is something here that depends on x. So we're not quite sure how well this will work. Don't think I'll comment on that one. There's another way you can do it. You can really remove the complete j from the equation just by taking the derivative of that first equation, that flux equation. And if you do, this is what you get. And if you at the same time remember that, well, yes, this is just the, there you can use this Poisson equation again. So you can plug in for that. And this is what you get then. So you can replace the first equation by this equation. So that's an alternative formulation of the same problem. The nice thing with this is, of course, you don't have to fiddle around with that constant. You're not quite sure if it is a constant or whatever it is. On the other hand, be careful with taking an extra derivative. You always lose something when you take a derivative. At least you lose a constant, which is actually what we wanted in this place. So we have tried to solve this thing, and we have tried to solve it the simplest possible way. And the simplest way is to approximate the derivatives by finite difference. So we have used central differences. For the second derivative, you use this standard second order central differences, and also for the first derivative, and a similar term for the derivative of that. And then the finite difference differential operators becomes a matrix T, which is this tridiagonal matrices, this standard tridiagonal matrices, divided by the step length there. And likewise, the differential becomes this discrete operator, the B matrix, which is that shouldn't be, it's not a plus, it's a minus there. This skew-symmetric matrix here, and like that. And using that matrix notation, you can write the discrete version of the equation like this. First you have a stand-up. What did I do? First I got a standard Poisson type equation here with the right hand side here. You have to take care of the boundary conditions, and I've just indicated, but they will be constant. We have Dirichlet boundary conditions here. So they are in this vector r sub phi and r sub n. The flux equation becomes slightly more complicated, but you can write it like this. And here I used MATLAB's notation. This is just, you take B times your discrete vector phi and throw in the boundary values, and you got the vector, and that vector is just a diagonal on a diagonal matrix. Take that diagonal matrix and add it to B and multiply by n. That's essentially your left-hand side of this thing here. And then your right-hand side becomes just this. The step length, there was a 2 in there, and there's the constant j, and this is the same for all equations. So you have this vector here. For the alternative formulation, where we have the derivative of this and the j disappear, you will got an equation like this. The headache is, of course, that they are non-linear. You can't solve them one by one and just feed it into your favorite linear solver. So you have to iterate something. That's not too difficult either. You basically have two choices. Either you can be lucky. Okay, I'll try hurry a little bit. Either you can try your luck and try some fixed point iteration and see if that works. But remember, fixed point iteration is not always, doesn't, definitely not always work. But you can write it like this. You just put on some iteration indices here. And if you have an initial guess of n, you can compute your phi. If you have your phi, you can compute next a new step of n. So you really iterate on n, and then you solve phi exact for that particular n value. And the same comes in both cases here. If you do the alternative one, where you have to compute the j, there was an integral to compute, and that have to be updated in each step. And you should do that by the Romberg scheme. And yeah, so that will be the full algorithm then. This slide should probably not be in there because I didn't manage to finish that on my flight down here. It's the convergence property are always tricky for this thing here. What you might see is that it looks like that nu comes into play. Is this correct? Yeah. Yeah. Look at this. This is the important thing. It appears to be that if nu becomes very small, then phi blows up, and you get into trouble with the convergence. But it isn't a proper convergence analysis. Let's see what happened. So this is one example. Remember, alpha was the left-hand side boundary. The right-hand side boundary of n was 1. Alpha equal the right-hand side boundary. That is the sort of silver to silver thing. And nu equal this, and we set up a potential like that, and it converges pretty smoothly and quite fast too. We tried the other one where alpha is smaller than nu, completely different potential here. But again, it didn't matter for the convergence at least. Completely different look of this. That's a misprint. That should be n, not p. Completely different shape of this density function. But it looks correct, and the convergence is fast. So then we tried, still that one is okay, but then we try an extreme different material thing here. And I just had to stop it after, say, 100 step. Nothing much happened. So so there's certainly something with convergence of this thing here. But if you, so you could try the other opportunity, and that is using Newton-Raphson method. You have to rewrite it like this. It's standard technique. It's a little bit of work to work out what the Jacobian is, but you figure that out. You can do that exactly. If not, you could have done it numerically. And you can compute the same example as just before. And this is how it should look like. So the Newton-Raphson converge also for this one here. So what's the lesson learned on this thing here? Basically, what we have done is on the numeric, that is that the fixed point iteration is easy to implement, and it converges. When it converges fast. It's not much work. Newton-Raphson is more. You have to set up the full Jacobian, and the Jacobian actually becomes a full matrix. You have to solve 2n by 2n system. So it's actually slower to use Newton-Raphson, but it does converge. We haven't yet figured out exactly how the convergence depends on nu, but it definitely does. And more work is needed here. I'm sure we should fix that over here. The physics, I didn't really go into this, but there is some large, the resistance in this stuff is of interest. And small value of nu give us large resistance. The future work is basically try to use the same model, but not only up here, where the really interest is in this area here, because that's where the really current is set up. That will require the same set of equation you can use, but you will have different boundary values. And notice that if you do set up an interval over here, you got something dramatic is happening when you move from one of these semiconductors to the other. So you really got a kind of a jump condition in the internal here. To model that effectively, you probably will have a non-equidistant grid, not an equidistant grid. That makes things harder, and you should probably rather try a finite element kind of work. Okay, that basically concluded how far my report on how far we have got with this work to this day. Yeah, so thank you.
Thank you very much, Professor Thor. Are there any questions? Questions? Okay.
Thank you, sir. I just want to understand, is this still work in progress or it's complete and some part of it has been tested in real time to see what the effect is?
Oh, it's definitely not been used any place so far. I definitely hope there are progress in the work too, but then more progress need to be done before we fully understand everything. And I would be surprised if some of those producing these solar cells doesn't have similar simulation tools. But of course they protect their cards pretty well, so he doesn't really know what kind of simulation tool they have. But but as I said in the introduction, of course you will have to make this in the lab in the end. But you can save a lot of work if you can throw away 9 out of 10 as useless before you really go into the lab. So.
They currently have.
No, we're not talking to any specific producers at this stage.
Okay.
I feel I need a better understanding myself of actually what's going on here before we can move to that. But of course, I see what you're getting at. That's when it's really getting interesting, isn't it?
Yeah.
Yes.
Okay. Thank you.
Okay.
Yeah, thank you. I want to find out how have you made an attempt to get assistance from your colleagues in the electrical and the physics department? If you have done that, then how have they influenced you?
Not really. It's a kind of very new work. It's done this fall, basically, this thing here. Yeah, I think it would be useful to talk to them, but I haven't done it yet. Yeah.
Okay. Yes.
Okay, well done for your presentation. I have a question in one of your slides. I just want you to clarify something that's, so I've not captured the number of the slide, but when you get to the alternative approach you used, I think a slide before that, the alternative method, the next slide.
Yeah.
The previous slide. Okay. Can you go again? Can you go to the previous one? Yeah, here. So with the flux in which you have over there, that's the last equation.
The last.
One. With the denominator. Could it be that with the denominator, when you find the integral, you are going to have an expression that involves a value that may go to 0 over there. So could it be that because of that limitation, that is why you use the alternative approach? Or what is the reason why for using the alternative approach?
I put the quotation mark. I mean, the assumption here is we have a steady state, meaning the flux is constant. The way I evaluate my sort of constant flux is through, well, these two are constants. But here, down here, I have my n, which, well, actually is a part of the equation. So that's sort of a moving object then.
Okay, so my question is, what happens when the denominator goes to 0?
It doesn't.
It doesn't go to 0?
No, that has to be some non-negative value all over the place. I fixed it to be 1 and a positive value alpha at the boundary, and in between you can't have a negative. It's physically impossible to have a negative density of these electrons here, in this physical setting here. So it might be 0 at some place, but not on the entire interval. So this integral will always be something positive.
Okay. My second, not a question, is just a request I'm making on behalf of KNST. When your project is complete and then you want to test it, I request that you come here to test it first, in Ghana, particularly in KNST, so that we'll be the first people to have the feel of it.
Okay. I'll take notes on that.
Okay, thank you.
Prof, could you please stay on that slide 12? I've seen that you are making some assumption that J is independent of X. Down there, you're also saying that J is constant.
Yes.
Could you please explain the two?
We're talking about this slide now.
Yes, please. You are assuming that J is independent of X.
Yeah.
That's right.
Yes.
And then you also say that when J is constant.
When J is constant, yes.
Yes, please.
Yes.
So could you please highlight the 2
Well,
points for me?
if J, yeah. Well, first of all, if J wouldn't be constant, I couldn't remove it out of the integration here. So that's the first place I need it to be constant. Then, if it is, yeah, and then I can turn it around like this. And then, if it really is constant, I argue again, well, then, well, this is a constant, whatever n is. You can integrate it, and you got one number. But then this nominator also needs to be constant. Means there must be some covariance here between the phi and logarithm of this, such that this happen. And if I do that, and I say, well, that is at least, that is to say, as you say, it is the same in every point x. And then I say, well, why not pick that particular point x I know the value in, which are the boundary values. So that's what I'm doing here. But there are some things half dubious about this constant assumption. So, yeah. So, but it gives you a reasonable thing, yeah.
Okay. At least your question.
Yes, Prof. I've seen 3D printed solar panels.
Okay, yes.
And it sounds like that's more easy because I can just go over to a 3D printer for them to print me solar panels for me to use in my home. And it looks like they have a package that you can actually fix things yourself. How sustainable is, if yours should come into production, how sustainable is it going to be as against what is already existing now?
To be honest with you, I have no idea. I don't claim to have an overview of what's out there, of other software products and other things. No.
Right.
So, well, honestly, I mean, I can advertise for this by saying at the end, far end out there, there might be a software product here helping people to understand this. But it's, to be honest, it's just as much an exercise for us to try to learn the process, what's really going on here, what's determining factor when you want to make a good solar panel. So, by doing this modeling and doing the computation, you also require a lot of understanding of the process. And I think that's, in particular from my student, and in this case I'm pretty much a student myself. I doesn't really, I'm an expert in this thing.
Thank you very much. Shall we give it up for Professor To? Thank you. Yes, I think we are far behind time. So now we move on to Mr. Cecil Humphrey. Please, you have, shall we welcome Mr. Cecil Humphrey? And he talks about DFT mechanistic study of zeolite catalyzed conversion of short chain alcohols in hydrocarbons. Yes. You have 10 minutes.
Hello? Okay. She's working. Great. Good morning. My name is Cecil, and I'll be speaking to you about the mechanistic study of zeolite catalyzed conversion of methanol and ethanol to hydrocarbons. Okay, so basically we are dealing with a problem of fossil fuels, and apparently this study that was conducted in 2015 by BP shows that the Earth's or the world's general energy consumption is close to about 86% dependent on fossil fuels. And as such, we need to find greener, more sustainable sources of energy. In light of that, we're looking at ethanol as a fuel. Now, after ethanol is produced as a result of fermentation of potatoes and corn, we could have one of two ways to utilize them. Either to mix them with some percentage of gasoline and then use them in modified vehicles, or we could directly convert them to hydrocarbons using two popular catalysts, that's platinum and zeolite. But the issue with platinum is that it's quite rare and it's an expensive metal, which means that it's not commercially viable to use platinum catalysts. So we're going to stick with zeolites, which is much cheaper. Now, zeolites can be defined as aluminosilicate crystals with a tetrahedral shape that is capped by oxygen molecules. Now, in the middle of the pyramid that you see over here, you could either have a silicon or an aluminium atom within them. Now, if the pyramid has the aluminium in there, you're forming, in actual sense, 4 bonds. And aluminium, as most of us might know, is trivalent, which means that there's a deficiency in the structure that you form when aluminium is capped with silicon. And to compensate for this charge deficiency, you throw in a couple of ions. Most of the time, you can use ions from the alkaline earth or the alkaline metals. Any of them will work. But for purposes of this specific study, we use hydrogens because we wanted to create an acidic environment. So ZSM5 is one of the most popular zeolites that have been used for this kind of catalytic conversion. And we've known that it works for a while. But the problem, one of the problems was actually identified by Schultz and Bannerman in 1994, where they were able to produce some amount of hydrocarbons between the chains of C3 and C6. But they realized that as the temperature increased and as the reaction went on, they ended up producing more of ethylene than the hydrocarbons. And they weren't able to clearly rationalize what exactly was going on. So then Algem in 2012 attempts to do a theoretical study to clearly identify what exactly happens in terms of reaction mechanism as to how the alcohol is converted to hydrocarbons. And he was able to study the dehydration of methanol to have an absorption energy of 18.5 kilocal per mole. The only flaw with his work was that the zeolite that he came up with was, he employed a cluster model, which means that you take the pore of the zeolite, put in potentials all around it, and then try and simulate for just one specific adsorption site. And in a real zeolite setting, you wouldn't have just one adsorption site, you have a number of them. So the fact that several experiments have been conducted on conventional catalysts that are being used, there's still that problem of how to form a precursor, which is the main thing that you need to propagate a hydrocarbon to form your long chain hydrocarbons. And that's the problem. So I set out to study the mechanism that is involved in breaking the carbon-oxygen bond so that you can have a hydrocarbon for which you can use in initiating the formation of the chain. Now, just as I've stated, my objectives were to study the mechanism of methanol and ethanol to the conversion of these alcohols to hydrocarbons using these two zeolites. Now, I picked ferrite because at the time, if we were to use ZSM5, it's quite large, and it would require a lot more computational power. But FER has similar framework features as compared to ZSM5, so I could use that instead of ZSM5, which is much smaller. And LTL also is quite similar to FER in the sense that they have the same number of atoms, but different framework features. So I was going to examine how the framework features are going to affect the conversion process. So the specific thing was to elucidate the reaction of the cleaving of the carbon-oxygen bond of the alcohol to create that precursor that I'm looking for. So the reaction scheme, or sort of like a roadmap to the calculations that I'll carry, are as follows. So I put my methanol molecule in, and then it's supposed to pick up a hydrogen or proton. Once it's protonated, the carbon-oxygen bond is supposed to cleave, leaving a methyl group. Now, the methyl group has one of two things that it can do. Once it bonds to a surface methoxyl group, or it creates a surface methoxyl group, an incoming methanol molecule could either bond through the carbon-carbon chain or through the carbon-oxygen chain. Now, if it goes through the carbon-oxygen chain, you end up with a dimethyl ether. If it goes through a carbon-carbon chain, you're able to create ethanol. So we've grown the methanol molecule, in essence, from methanol to ethanol. Now, if this progresses, you could either have the beta carbon over here of the ethanol molecule interacting with the vacant adsorption sites, or you could have the alpha carbon over here interacting with the vacant sites. If it's through the alpha carbon, you end up creating a surface ethoxyl group, and then you eliminate water here, which is more or less the dehydration process we're talking about. Or you could have the elimination of water from here, and then you're forming a carbocation. Now, the hydrogen on this end of the carbocation, if it's flipped such that it's in close proximity with the surface oxygen over here, you end up creating ethylene, which was what we studied, or what we observed in Schultz and Bannerman that I mentioned in that literature. So, in essence, I used density functional theory as in my methodology, which is in the Quantum Espresso package, with a plane wave basis set and then ultra-soft pseudopotentials developed by Vanderbilt. And then for the exchange correlation functional, I use generalized gradient approximation with a hybrid functional of Padyubek-Einzinoff. And then visualizations of the structures and the electron densities was conducted with X-Kristen, P for VASP, and Vesta. So then this is how a zeolite structure looks like when it's fully optimized. And then I picked pore A because it is the only pore that is large enough for me to propagate my chain, which I intend doing. And this is us viewing the structure in the 001 plane, which is the Z plane. This is another one, which is the ferrite structure that is fully optimized. And again, I picked A because it has a cavity diameter of about 9 angstrom, which again is large enough for me to propagate my chain. Then I had to compare the optimized structure of the zeolites to what already exists, because we have 3D X-ray crystallographic images of the actual natural zeolites. And based on the table, as you can see, I compared the results, and it corresponds quite well with what is observed in experiments, which means that the level of theory I use clearly defines an actual real zeolite environment. Then I went on to sample the different adsorption sites. So for LTL, I had a number of adsorption sites, which would be 6. And then for FER, I had 4. And from the FER, the graph for the FER, you can see that the most stable site for FER is actually site 4. And then for LTL would be 1. So I picked those sites, and then I'm going to focus on those specific sites and then try and elucidate the dehydration process. Now, this is a nightmare for all theoreticians. When an experimentalist proposes something, for instance, place the methanol molecule inside the pore, and what we are anticipating is that it picks up a hydrogen. Well, unfortunately for me, mine didn't work. I placed the methanol molecule inside the pore, expecting that it picks up this hydrogen, gets protonated, and then there's a cleaving of the carbon-oxygen bond. That did not happen. Instead, it sat at a very safe distance from the adsorption site, and it's held in place due to long-distance and short-range hydrogen bonding between the hydroxyl end of the alcohol and the adsorption site. So then I sat back with my supervisor, who happens to be the chairman for this conference, Professor Evans Ade, and we're thinking. Now, I looked at dynamics in the sense of this whole work, and then I realized that the deprotonation energy, which is the minimum amount of energy required to remove one of these hydrogens from its actual site, is actually lessened once you increase the temperature. But the thing is, I can't use dynamics to study the transient movement of electrons. So then I have to revert back to DFT. But the problem with DFT is all of the calculations are carried out at 0 Kelvin. So what I decided to do is I changed the initial geometry, and instead of trying to get the methanol molecule to pick up the proton and then get protonated, you place the proton onto the methanol molecule and flip it such that its orientation has the carbon rather interacting with the adsorption, the vacant adsorption site, instead of the hydroxyl end. And this was the end result. It turns out that the dehydration actually does occur. So the carbon-oxygen bond cleaves, leaving the surface methoxyl group, which you see at the top here. And this happened at an energy of minus 11 kilocal per mole. And the same thing was observed in the different zeolites. I then went on to try and then form the ethanol molecule by introducing another incoming methanol, which would bond through the carbon-carbon. And this is represented by the black balls that you see over here. And I was able to form ethanol molecule, which was at minus 46 kilocal per mole, which is quite stable. And then I went on to do the carbon-oxygen linkage over here. And then I was able to form a protonated version of a dimethyl ether at minus 25 kilocal per mole. And these are the results, having obtained or having been able to grow the methanol molecule to the ethanol stage. I happened to experiment with a number of different orientations inside the adsorption sites just to see the adsorption, sorry.
1 minute.
Okay. Just to see how it would interact with the sites. And these are the adsorption energies that I obtained. But the key part is the ethanol molecule was interacting with a beta carbon, and I was able to produce the carbocation that I intended, which is the precursor for the formation of the chain. I also got a surface ethoxyl group at minus 16 kilocal per mole. And this is the first time it's been observed in theoretical work. Now, in conclusion, the absorption energies are more favorable in FER as compared to LTL. And then both alcohols had to be protonated first before we actually witnessed the dehydration occurring. And then the protonated ethanol molecules forms a carbocation or a surface ethoxyl group, depending on which carbon interacts with the vacant site. And then the carbocation and the surface ethoxyl groups are the precursors that we require. So in essence, we got methanol to produce ethanol, which in turn produces a carbocation for the long-chain hydrocarbon. Thank you very much. I'd like to acknowledge these people for the sponsorship. And these are my references. Thank you.
Thank you. Thank you. Are there any questions?
Okay. Thank you for the presentation. I really liked it when you started with the energy issues, because Ghana is highly deficient in that. So I thought you were coming up with some new stuff that we can add to Ghana's energy mix.
Yeah.
but it turns out to something else. Can you link what you did a bit to how energy can be produced from? I saw the fermentation of potatoes and maize and all that.
Yes, so we have depleting, and this problem is not necessarily limited to Ghana. It's an international problem that we have depleting resources, fossil fuels in particular. And the main issue is you want to come up with a greener form of energy because the fossil fuels are not doing any good to our atmosphere. So then this is sort of like an area that is normally governed by chemical engineers and material scientists. And the main stumbling block to enhancing us converting alcohols to hydrocarbons, which would be an alternative source, is that precursor. Nobody has obtained it. It seems to be a problem, and because it's quite cumbersome to go through those specific reactions, everyone skips it.
Okay. Be based on these food stuffs, because agriculture has also its own problem.
Yes, it's bioethanol. So wherever you can get the ethanol, it doesn't really matter. We can synthesize ethanol in the lab. You don't necessarily have to wait for corn to ferment.
Okay.
So it's just saying that if you get alcohol, I can change it to hydrocarbons. Basically that.
But in your own point of view, do you think it's cost effective? I mean, when this thing is being put into practice?
Yes, it's very cost effective because synthesizing a zeolite for something like this is very cheap.
So what are you doing to promote, something like this?
Publish.
Okay, thank you.
Thank you. Any more questions?
Okay, thank you for your presentation.
You're welcome.
You mentioned in the beginning of your presentation, you're like, you want to throw in hydrogens just to create an acidic condition.
Yes.
Why acidic condition?
Silicon-aluminum ratios are what dictates the acidity of a particular environment. So if you're able to produce a higher number of hydrozonium ions, then technically you have a very, very acidic environment. So if I'm putting in protons or hydrogens, what I'm trying to do is to get them to protonate the alcohol so that it cleaves. And that's basically the acidic environment, the essence of the acidic environment.
So it can't work in any other condition apart from the acidic?
No, if you use any other ion, it wouldn't be favorable.
Would it be favorable or it doesn't work?
It does not work.
Okay.
Thank you very much, Mr. Cecil. Shall we welcome our next presenter, Mr. Henry Martins? He speaks about modeling of metallic crystals for industrial applications.
Showing. Nice. Okay, thank you. Good morning. I'm Henry Martin, and I'm here to present on modeling of metallic crystal for industrial application. This work is actually ongoing.
Please, can you speak louder?
This work is actually ongoing as I'm working as a PhD student in NIMS. I don't really know what to say, but because today's lecture looks like all the speakers have said what I'm about to say, but I'll try to just say a little bit that I can say. This will be my outline. We all know that in our daily activities or in industrial applications, we use metals in doing everything. The roofing of this place, in our cars, even in our homes, we have our knives, which has metals. But then what about the process that takes place in producing these items, that is this metallic substances? What happens? We have two main processes, which is first obtaining the compositions, as in bringing these materials together, whether carbon, iron, or molybdenum, or whatever. We bring it together, and then first we have the industrial process, which is softening and hardening. That is, we heat the metals or these materials to a high temperature so that it becomes liquid form, and then we either quick cool it down or slowly cool it down, which in that case is going to give us the mechanical properties, whether the ductility, the strength, or the toughness. In that, then we'll be able to know whether we'll use it for the car or use it for railway or for the knives that we use. So what we actually intend to do is that over the years, obtaining these mechanical properties is in a difficult way so that they are not able to really get this hardness or the ductility. So they undertake a lot of experimental activities during the process. So when we are heating it to a specific temperature, after that, and you are going to cool it, you need to test and see whether it's having the required mechanical property you have, then goes down. So they'll go through all this process. But that is very tedious because you are going to have a lot of time wasting, and then you are going to have a lot of money involved to do all this testing. So what happened that they decided to now start to save these informations. So they have what they call the atlas. Then when they want to know the specific ductility, they go through this atlas. They will know the required composition for that material, and then the temperature or the time that they're going to cool or heat for this material. But going through all this process, we see that there is a need that we have to have some kind of computational effort so that we can reduce this timing and going back and forth. Just like I said, the other speakers have said all that already. So we first look at the statistical modeling, which is to mimic this atlas so that they will not be going back and forth, or in the sense that they need to produce a new material. Probably based on the environmental condition, the material they have produced is not able to withstand it. So how do they go about it? So just to input this kind of data into the model, they'll be able to have the atlas and then quickly do the production. Or go by the multi-scale modeling, multi-scale modeling, which will be able to give a more understanding upon the plasticity of the metal, as in with the plasticity, we'll be able to determine the mechanical properties. So we start with the phase one, which will be the statistical modeling, and as I've said, just to mimic the atlas. So in doing that, we go through this process, which we have to just acquire the data from these various atlas they have, and then we also view whether what we have extracted is the same as what is in the atlas. Then we formulate our model, and then we write some code for it. So this is just a typical example of how the atlas look like. So if you see at the top here, they have the fractional composition in the mass concentration percentage, and then the temperature, and then the time. So these lines here are just the cooling rate. As I said, like they cool it, and then this is when we are having temperature, and then with time, which I said, either you cool it rapidly or slowly. So after extracting, we first looked at the onset of ferrite, which is mainly the first percentage which we will have here, which will look like this. So after we extracted the data, then we noticed that, as you can see from here, most often every atlas has this chemical composition. So it means that to every atlas, there is this constant composition. We do not change. So that is one assumption that we have in mind. And then this is mainly the composition that we took for this work to really understand what is going on. And then we decided to use this longitudinal data analysis because we have a lot of data samples and the time are in a repeated manner. So in developing our model, we first looked at literature, and then we saw that in recent times, that is in 2010 and 2012, there has been some publication in this area. But then what is lacking is that they all actually look at their composition in the form that they do not interact. But we all know that to have materials, there's just going to be some kind of bonding. So there's going to be an interaction. So we need to figure that into the model. And that is what we decided to do. So we use this equation in doing that. So then, as we have also seen from the atlas or this profile, we can see that it's in a way as an asymptotic regression. So in order to capture this form of asymptotic regression, we sought to use the Gompers function here, which we see here in equation 2 here. So we first of all ran the one that has been done in 2010 by Santos, and then we saw that with their quadratic form of interaction, there are some kind of results here that are not really significant, as in they do not play much role in this form. And then with that of the one in 2012, yes, they only looked at just 2 interactions here. And yes, it's significant. But we decided to just move ahead of it because it's a whole lot of composition. So why do you just only figure out with just these 2 interactions? Which we looked at it in various ways. And as you can see here, most of all the ones we have found is significant. And that is to say that unlike these 2 recent forms of statistical model, we can further go ahead to find an interaction for this modeling or to mimic the atlas, and we'll still have a better results. So then from there, now we are on the multi-scale modeling. But before I take you through it, I would like to just give some kind of physical processes or phenomenon with this multi-scale modeling. First of all, we already know that with crystals, there are so many forms of crystals, depending on the material you are using. So we can have the BBC and then the FCC. But in the plastic deformation, as in determining the mechanical property, when you have the heat, this is the heating it to a very high temperature, which is the austenite, it's deformed to this way. And that deformation is where they are going to get that particular property from. So the idea is that there's going to be some form of stress, some form of thermal activation to these specific materials. So what do we do to this? What happens then? With that, this is just a cubic form of it to explain some things or some processes that take place. As I've said, the first one here is the point defect, which have, I think, 3 forms, the interstitial and then the substitutional. The interstitial is basically something like this, where you have carbon, very small atomic size elements, fitting into the interstitial part of large elements. And then we have the slip, that is when the stress is applied onto this material in the direction which is parallel to the surface of the material, then it causes some kind of a slip to it. And then the tuning, and tuning is when there's some kind of, after the deformation, you can see some kind of a mirror-like shape with the the closely packed molecules in that form. And the tension and then the compression has to do with when the force is applied onto these things, the size of this plane, specifically this plane here, can shrink this way, and that is what we're calling the compression, and then the size in this direction, the Z direction, can also move up, and that is the tension within the system. The partial dislocation and the stacking default has to do with how closely packed these atoms are. So, meaning that we are changing the orientation, just like you see from here. The orientation here has been changed to this way. So we need to have all this in the model that we need to do. This is just to say that, just like the lecturer was saying, that you need to add the physics to the mathematics. So we need to go back to the point where we will be looking at from the atomistic state always to the continuum state before we can have the movement, as in the formation of these dislocations, and then now it starts to move, and then whether when they combine, what happens to it. And that is what we intend to do by using the multi-scale modeling, starting from the atomistic state all the way to the continuum state where we can have the real model. So we are combining all the way from the atomistic state. So with that atomistic state, I think the one who just said has even said a lot about that already. It is just a numerical ab initial electronic structure, which is also called the first principle, to look at how the electrons within these materials move, and also to extract the energies, the forces, the stress that we need. We are going to extract it from this particular side of the multi-scale level, which the other speaker said he used DFT. Yes, that is the same thing I'm going to use, is just from these three principles here, looking at the position of the electrons and the nucleus, and then we try to look at the repulsion and the interaction. That is just from the principle of Schrödinger equation, and then from some kind of approximation techniques, which he mentioned a lot of them here. And then we move to the other level, which we call the microscopic, mesoscopic. That is to capture the defect or the deformation within the dislocations. And as I have explained, all these variables here, or all these terms that happens, we using it in the form that the kinetic Monte Carlo. Most people use the molecular dynamics form, but recently it has been seen that the molecular dynamics form are not able to capture some kind of time formation within the dislocation, meaning that it is very fast, so they are not able to capture it. And that is why we look at the kinetic Monte Carlo, which deals with probability, just like the way experimenters did. Experimentalists take their data, sample it, and then average it over time. Okay, so with that, we then move on to the microscopic, which we finish with it. That is the continuum level. And then we follow these three main principles from the initial, which is the reference point, and then we look at the lattice structure coordinates, and then bring it into the deformed part of it. Thank you.
Thank you. Thank you, Harry. Please, are there any questions? Okay.
So many questions.
Thank you very much for your presentation. Please, can you go to figure 9? I didn't actually get the page. Figure 9. Yeah. And before that, figure 8, you made mention of BCC and FCC. Then I want to find out if you also try considering the HCP, since the HCP and FCC, they have some similarities, but then the stacking sequence, they're a bit different. So did you take that one into consideration?
Thank you very much. As I said from here, depending on the material you are using, you would get these specific crystals. And it also depends on what application you want to use it for. If you are looking at maybe railways, or you are looking at big machines, then you are going to narrow down to your choice of element. Okay, so I'm not looking at all the elements, or I'm not looking at all the application form. For this work, which I said it's ongoing, we are actually looking at BBC alone here with an incorporation of carbon. So more like molybdenum with carbon or iron with carbon. And that is to target a specific application. Okay, I don't know whether I've answered your question.
Yeah, please, one more question. Yeah. And with regards to the atlas that you're trying to simulate, to follow, that phase diagram, I want to find out, does it contain that of the binary, the ternary, because we have different phase diagram? Does the atlas have all these phase diagrams?
Yes, this is ternary in the sense that you have two more compositions, more than two compositions from here. There are more than two.
Okay, thank you.
Okay, the next question.
Thank you very much for your presentation. With the statistical data analysis,
yes.
I want to know how you selected your model, because at least there should be some justification.
Yes, that is assumptions. Yes, so like I said, from it, we look at the atlas here. So first of all, we know that this composition results in this atlas.
Excuse me, please. Are there other models, I mean, apart from the one you chose?
Yes, as I said, in recent times, we looked at, sorry. Presentation mode. Oh.
Can you just move on?
I was looking for the presentation mode, but I can't find it, so you let me just go on. Yeah, this is the two, I think your question was, are there any other publications, right? Models, yeah. This is just to show the two models that are in existence. That is in 2010 and then 2012. Okay. But as I said, their model was looking at this first model look at the square of this element or compositions. And this model tends to look at only these two interactions. Okay, but the whole idea is that we know that it's not just going to be only these two interactions, which is this 2012, or even to look at just the quadratic or the square form of this interaction. So we need to have more interactions. And that is what we have incorporated in the model. So that is the difference with ours and the existing model here, which is this first one and this one. These are the recent ones, of course.
Okay.
I didn't go to, we're moving forward.
Thank
so
you,
what is forward is
Mr. Henry Martins. Shall we give it up for Mr. You can, if you have further questions, you can contact him and then follow up the questions. We shall go for our snack break and come here at 11:45. Meanwhile, if you have not presented your slides to Pat, please do so whilst we are on the snack break. Thank you. See you here at 11. Yeah. time now? 11:50. Please, we are coming back at 11:50.